Hi, I'm Chris O'Brien. Thank you for joining today. I'm a partner with Exida Consulting, and I've got over 25 years experience with process automation, DC power systems, and functional safety. So again, I'd like to thank everybody for joining us, and let me just tell you a little bit about Exida. We're a consulting firm, and we help our customers in several different ways, but primarily ensuring that they design high reliability, high availability equipment and systems. We can help with training, reference books, providing expert consulting. We can help on projects with lifecycle services, taking over a bigger part, and we are an ANSI accredited certification body. We have offices around the world in most of the major technical locations, so we are close to our customers. And as I mentioned, we're ANSI accredited for cybersecurity as well as functional safety assessments. And that can be components, products, systems, architectures, or people. Publish a lot of reference books, including some very detailed and complete reliability handbooks, both for complete equipment and components. So let's get back to our main topic, which is proof testing. So again, proof testing, for those who remember from a couple weeks ago, or maybe if you're new to the series, proof testing is an important part of achieving the desired risk reduction and functional safety. It's required by the functional safety standards, and we see because of that requirement, more and more companies are implementing comprehensive programs to do it, but often there's quite a bit of confusion as to what proof test coverage a person should claim for a given safety instrumented function. So today we're going to look at how you will determine what proof test coverage you should give a safety instrumented function. So the purpose of a proof test is to detect any failure that is not detected by automatic online diagnostics. And those failures could be dangerous failures, diagnostic failures, parametric failures, and also you want to detect unauthorized program changes. So if it's a type B device, smart device, you want to be sure the programming hasn't been changed. So when you're designing these things, it's very important to know what you're trying to test for. If you don't have a strategy and you don't know what failure modes you're looking for, it's very difficult to design an effective proof test. And I would define an effective proof test as one that gives you the improved safety you want with the right balance of cost. You don't want to not test something and be unsafe, nor do you want to do a lot of testing that actually isn't finding those failure modes you're looking for. We discussed in the first webinar the concept of a tiered failure structure, where we could, at the far left, we could tell, did the function work or not? Is it okay or is it failed? And at the far right, we're down at the component level, or the things that are used to build the equipment. So if we take a ball valve as an example, at the component level, we could have the actual ball, and it could have several failure modes, such as binding, fracture, could have a minor leak or a major leak. That component and other components are used to build up the ball valve or build up the device, and each component is going to have certain failure modes and failure rates. Tier 2 is the functional level to say, at the valve, what do we observe as the failure mode or the functional failure mode? You could have failures that have no effect on the valve's performance. You could have failures that result in excessive force being required to move the valve, etc., etc. What we want to do is we want to build those through and be able to trace component failure modes all the way to operational failure modes. You know, the most important thing we need to know is, did the function work or not? But the next very valuable information is, how did it functionally fail, or how could it functionally fail, because that's going to inform us on how we design the proof test. So if we continue with our example of we'll take it as a final control element, and what we're going to build up today is a floating ball valve connected to a Scotch yoke actuator that's driven by a three-way solenoid valve. We can envision at least 5 different proof tests for that assembly. Proof test 1 is a partial valve stroke. Proof test 2 is a full valve stroke. Proof test 3 is a full valve stroke at operating conditions. And then for proof test 4, we take the full valve stroke and add a leak test. And then for proof test 5, it's a full valve stroke at operating conditions plus a leak test. To determine the effectiveness of those different tests, we need to have a good failure rate, a baseline failure rate for each device. So we'll perform an FMEDA with the functional failure modes to get the functional failure modes. We can assign coverage as a function of the failure mode, and then we can allocate what's found between, or distinguish between what could be found if a test is run as a diagnostic or if the test is run as a proof test. So here's an output of over 33 different floating ball valve FMEDAs we've done. And if we take and look at, take a 90% cutoff rate, we see that 575 fits will cover 90% of the designs that have been evaluated. So that would be a reasonable place to set the generic failure rate number. So we do that, and we do our detailed results that we looked at in our last webinar. And we look at, on the top of this chart, we're seeing what we call functional failure modes. So we have excessive force, loss of drive, and leakage past seat for this example. This example is just the floating ball valve. So of the total failure of 575 fits, 335 are failures that would result in excessive force being required to move the valve. 25 would result in loss of drive of the ball, and 215 would result in leakage past the seat. And for our 5 defined proof tests, we then assign our proof test coverage. And 61508 gives guidance for low, medium, and high effectiveness testing. So for low effectiveness testing, you give it a coverage of 60%. For medium effectiveness, you give it 90. And for high effectiveness, you give it 99. So we assign the coverage by the test against the functional failure mode. And then we can determine what would be detected. Let's say these were done as an automatic diagnostic, what would be detected and what would be undetected. We need to remember that these tables are going to look different for different applications. So this table is valid for a close-on trip, but wouldn't be valid for a tight shutoff application or an open-on trip application. So extending on that, let's talk about an automatic diagnostic versus a manual proof test. Take a look at some non-SIF related failure modes, and then take a look at an example of how we could build up the proof test coverage for a complete assembly. So, mode of operation is something we need to take into account because it informs us as to whether we can, first it informs us whether we need to use probability of failure per hour, or we can use PFD average, the average probability of failure on demand, and whether we can take credit for diagnostics and proof testing. So most process applications are going to be in low demand, meaning they have a relatively infrequent demand on the safety system, and proof testing is conducted relatively frequently. So the average, our definition, Exida's definition, is the average, you're in a low demand condition if the average interval between a dangerous condition, a demand on the safety system, occurs infrequently, for example, once a year or longer. The automatic diagnostic testing interval is an order of magnitude lower, and the demand interval is greater than 2x the manual proof test. In this case, we can take credit for diagnostics and we can take credit for proof testing. If we look at the modes from the standards, In 61511, we talk about two modes, demand mode and continuous. In 61508, that's broken into three, low demand, which is the same as demand, high demand, and continuous demand. In demand mode or low demand, we can use PFD average, and we can take credit for proof testing and automatic diagnostics if they meet the criteria of being at least an order of magnitude faster or more frequent than the demand rate. In high demand, we take, in either high or continuous demand, do we take credit for proof testing. We also use the probability of failure per hour from the tables. We can take credit for diagnostics in high demand if those diagnostics run quickly enough, but we take no credit for proof testing or diagnostics in continuous mode. Diagnostic capability is measured by a coverage factor, and that's the percentage of failures that would be detected. So CS is the coverage factor for safe failures, and CD is the coverage factor for dangerous failures. Automatic diagnostics are important because detected failures can be mitigated. For example, if a dangerous failure is detected, we know the SIF will not respond to a demand, and the system can be designed to trip if the impact is not significant. Where we see that are applications like machine safety and robotics, where there's a relatively simple restart in process. It may not be done that way because it could first and foremost introduce additional hazards, or it could be very costly. So you may use redundancy, or you may use implementing an additional means. If option one, to trip, is not reasonable, then you could enunciate the failure so operations can recognize the SIF and take alternative safety measures. There's what sometimes seems to be a disconnect or a negative impact of good diagnostics. So you can in fact you can look like you're lowering proof test coverage by implementing diagnostics. So this table here is the table we looked at with the functional failure modes and the proof test coverage. Down here we've got a table that says, well, let's say we did proof test 1, we would find 201 dangerous failures. So if we only did that as a proof test, the proof test coverage there would be 201 over 575, which would look about, it'd be the high 30s. If we implemented a partial valve stroke test as a diagnostic and then a full valve stroke test as the proof test, we would only find 100 failures. Now, in total, we still find the 301, but 201 of them are found by the diagnostic. So now we're only going to have 100 failures, or we're going to have 100 failures is what we detect, over 575 minus 201, which is 374. So the proof test coverage is going to drop. We're still finding the same dangerous failures, we're just seeing a lower proof test coverage. So it doesn't actually, it seems when people go through this, it seems like it's degrading stuff, but in fact, you do get a slightly better PFD average because a dangerous detected is going to be acted upon more quickly than something just found in a proof test. So that's kind of a interesting byproduct of improving diagnostics. They do improve safety. They can just looks a little counterintuitive. Now, if we look at what we would call a strategic proof test we define as something that's done that balances detecting dangerous failures with giving you the right amount of safety coverage. So we want to do this because we can design proof tests that are easier to do, cost less to do, and frankly, when that happens, they're more likely to get done. if we understand dangerous undetected and enunciation failures, we can improve our test coverage as well as lower costs. And we can use program changes. We can detect program changes or changes to configurations via tools or configuration revisions in most that are available for review in most products. If we want to go from an individual device's proof test coverage to an element, we're going to need the failure rates and the functional failure modes for each device. We need to assign the proof test coverage for each functional failure mode, and then we need to add up the failure rates and failure modes for all the devices in the final element, which we'll get to in a minute. Now, there are additional failure modes and mechanisms that can be in a device that are not related to a safety instrumented function, but are related to safety. A common example of this would be external leak. So an external leak, if the function of the valve is to stop gas flow in a line to a boiler, and it closes, that's good. It's going to stop that flow. If it's got an additional failure mode, such as a leak through the casting, the sieve could still perform its task, but that leakage creates a secondary hazard. Now that hazard isn't associated with the sieve, but it should be considered as anything of that type should be considered as part of an overall mechanical integrity program. So we can think of a proof test as a subset of the overall mechanical integrity program. When we're designing our proof tests, we want to take information from the SRS, the safety requirement spec, and the safety manual. So the safety requirement spec is going to tell us things such as what leakage is acceptable, what are the timing requirements. So for example, it might specify the final element must close to IEC 60534-4 class 3 leakage within 180 seconds. If you don't have a specification such as valve must close is not sufficient to design a test to. And if you're not timing something, you don't know that you've achieved the safety reliability or you've achieved a state that does bring the process to a safe state. So this is a really important thing to tie out in all specifications and all testing. So let's take an example. Let's take an example where we're building a final control element out of a floating ball valve, a Scotch yoke actuator, and a three-way solenoid. So here we've got our valve, actuator, and solenoid. We have the same failure rates that we looked at previously for the valve. We've got failure rates now for our actuator and failure rate for our solenoid, split between the functional modes. So for excessive force, we've got some things that combine in the valve and the actuator. Insufficient return force, we could have a weak spring in an actuator, or we could have a reduced output flow in a solenoid. So it's got reduced capacity, which means it may not vent. So we're going to assume it's, in this example, it's a spring return. So that failure mode would be the solenoid does not vent quickly enough, so the actuator cannot move at the proper speed, so we don't close essentially in the time we need. And this is a case where timing the response of the final element is important, so you show that it's closed and done what it needs to do. Then we could also have a failure mode of loss of drive, where this could be a breakage of a stem in the actuator and the valve, or it could be a complete clogging of the solenoid output, and then leakage past the seat. So we can take our functional failure modes for the assembly, we can take our proof test coverage versus functional failure modes, and then depending on what proof tests, or what tests, we'll call them PT1 through PT5, what tests we implement, we're going to get different results. So if we implement a test as a diagnostic, what it does is it allows us to recategorize a failure from dangerous undetected to dangerous detected. In our first example, we're not implementing any diagnostics, and we're going to do an annual proof test to function 1, which is the partial valve stroke test. So in this one, we have no diagnostics, so nothing is designated dangerous detected. All of these failures are still dangerous undetected. We implement a partial valve stroke test as the proof test, so we get 60% coverage on the functional failure mode excessive force, which means we detect 603 failures, and we get 32% proof test coverage. Our second example, we're going to do a full valve stroke test. So this top up here is going to remain the same. Down here, we still don't have a diagnostic, and now we have a full valve stroke test where we get 90% coverage for excessive force required and insufficient return force. That shows that we find 1,067 out of 1,875, or our proof test coverage goes up to 57. So that's improved. It's a more complete test, and not surprisingly, the proof test coverage is better. In example 3, we implement the partial valve stroke test as a diagnostic, and we implement an annual full valve stroke test. So now we find 603 fits, or 603 failures per billion hours, as a diagnostic, and they're now recategorized as dangerous detected. Our dangerous undetected now is 1,272. Our proof test coverage, now we found 60% of those excessive force failures when we did our diagnostic. We're going to find 30% of the original number when we do our proof test. We still find 90% of the insufficient return force because, if you remember, proof test 1 didn't tell us anything about that. So now we find 464 out of 1,272, or our proof test coverage drops to 36. Now, we can see, if we compare the results from example 2 to example 3, we're still finding the same number of dangerous failures in both instances, which makes sense because we're essentially have the same amount of coverage. We've just broken that coverage into 2 parts in example 3. So in example 3, some dangerous failures are found during the diagnostic, which allows them to be recategorized as dangerous detected, and some are found in the annual proof test, but the sum of both of them is equal to the original number. So the math is correct and it's modeled correctly. In our final example, we're going to take and use a partial valve stroke test as a weekly diagnostic, and then, this should be proof test 4, sorry, that should say 4. We're going to use a full valve stroke test with a leak test as our annual proof test. So we calculate and assign some as dangerous detected versus dangerous undetected, and then we calculate our proof test coverage, which is a 90% because we've got a very good test regime in that case at the end. If we look at the PFD average results, they make sense, they follow and make sense as well. So in example 1, we had no diagnostics and a partial valve stroke test. We modeled this, I think, with a 10-year mission time. So we had a PFD average of, 5.67 e to the minus 2. In example 2, it's a full valve stroke test, so PFD average improves, lowers, so it's 3.97 e to the minus 2. Example 3, we have proof test. We have a diagnostic of a partial valve stroke and a proof test of a full valve stroke, and that's a little bit better. It goes down about 6 or 7%. And in the final example, we have the partial valve stroke test as the diagnostic and a leak test, full valve stroke with a leak. So we see quite a bit of an improvement there. And you can see, now this could inform you to say, oh, well, I'm not, in the way I designed it, I'm not picking that much up with my full valve stroke test or partial valve stroke test as a diagnostic um, over just doing an annual proof test. Or, wow, depending on what you need from a performance perspective, you can model these different scenarios and then implement the one that helps you achieve the reliability and availability you need. This is the PFD chart for the final element, and it's a comparison of example 1 in the upper left to example 4. And what you can see, the first thing you can see is this little bit of the height of this reduction at the proof test is a good indication of the effectiveness. So we can see where we did the partial valve stroke test, it really didn't bring it down that much. But when we do a leak test, it's quite a bit better. And the other thing you can see is if we look at how high the first arch goes, it's an indication of the dangerous, failure rate. So here that arch goes higher, meaning that the dangerous undetected failure rate or the dangerous failure rate blend is higher. Here some of those failures have been recategorized as dangerous detected, so they have a lower impact on the PFD average. Now, all proof tests, another requirement is that proof test records are recorded and reviewed. So actual testing must not only be done, but it must be documented. Those documentation should include the test details, title, version number, etc., what personnel conducted it and the date, was any bypass authorization needed, record as found conditions, then perform the tests, review the results, and restore the system to run condition. So that's a little overview of some things to consider in designing tests. And now we've got some time for questions. So, oh, there's some questions. So, okay, so here's a question. On an Exida certificate, a fail detected failure is defined as what? I usually have trouble defining it on silver. Okay. So the question is, a dangerous detected as defined on a piece of equipment, and what to do in configuring that in the Excellentia tool silver for detected or not. So if we have a transmitter and, well, let's start with a valve. So a dangerous detected, if we take a solenoid, an actuator, and a valve, there's no intelligence in those products to run, say, a partial valve stroke test. So what would happen is that would be implemented in an application diagnostic, and which means we'd program the safety PLC to do it, unless somebody used a smart positioner with the capability. So you would configure the safety PLC to run that test, and you wouldn't need to change anything on the configuration set up in Excellentia for the PLC. I think this question is more on a smart transmitter where there's a failure mode that says dangerous detected. So if we're looking at a smart transmitter, dangerous detected would mean that transmitter has a internal diagnostics and has the ability to look for faults and then to drive its current to the predefined upscale or downscale current level. Usually, I think it's 21.5 milliamps upscale and maybe 3.6 to the Namur standard downscale. Now, some companies redefine that a little bit because they can't go quite that low. But what that would mean when you click PLC diagnostics, when you're configuring an input, it implies that you've configured the input block of the safety PLC to read let's say 21.5 milliamps as the example, 21.5 milliamps as a transmitter dangerous detected failure. So if you were voting that as a 1 out of 2 or a 2 out of 3, you would basically take that, in the 1 out of 1 out of 2, you might degrade to a 1 out of 1 for your repair time, mean time to restore time. In a 2 out of 3, you would probably treat that as a vote to trip. But if you don't click that box in Excellentia, it basically treats those dangerous detected failures as dangerous undetected, because by not checking the box, you're saying the PLC doesn't know 21.5 milliamps from 19.8 milliamps. It's just going to read it as a valid signal. Let's see what other questions we have. Oh, so person would like to go back to the different proof tests. So I'm showing that. Maybe that'll prompt another follow-on question. Oh, there we go. So I'll leave that up. Well, question, what part of 61508 gives guidance on level of effectiveness for proof testing? 61508, I don't know off the top of my head, but it would be actually level of diagnostic coverage or test coverage, and I think it's in, I apologize, I don't know off the top of my head, but it does define low, medium, and high effectiveness. I just don't know the section. So what we do is we take, and when we're doing an FMEDA, we assign either no coverage or low, medium, high effectiveness coverage for a defined test for a functional failure mode, and then add that up over the entire product to get dangerous detected, dangerous undetected, and the effectiveness of the different proof tests. Why are the tests, partial valve stroke test and full valve stroke test, at operating conditions unable to detect any loss of drive failures, and when you get a leak, you're given 99% coverage? Okay, that's a great question. We've defined loss of drive as inability to move the valve obturator. So in this case, the ball. So we could have a failure where there's, well, let's say that the valve stem shears, and now it's in 2 pieces. I can't think of a case where it's not, but I'll say almost always the position feedback on the actuator stem is taken from the side. You have a stem going through the actuator, down the bottom, out the bottom of the actuator, it goes down to the valve. Out the top, it goes to a position indicator or a position readback. So the actuator stem could be turning, but the ball plug, the ball is not turning. So the stroke tests don't tell us if the plug actually turns. The one indication that we have that the plug has actually turned and closed off would be flow. So if you stroke the valve and check that there's no flow, you've shown that you have drive all the way through the plug or the ball valve. Given a sensor, is it reasonable to have a proof test coverage of 90% or higher if you exercise it through its whole range? If not, what are some examples of undetected failures that are still not covered? So, let's take a smart device, and it still may be reasonable that you get above, well, this is where the safety manual really is going to be helpful in the FMEDA, because they're going to give you recommended proof tests. One of the things that 61508 says needs to be in a safety manual our recommended proof test, so that should be there. So we could imagine, I don't know I can't imagine the numbers off the top of my head, but I can imagine the scenario that certainly exercising the sensor will show, through 0 to 100%, it's going to show the sensor's working, it's going to show that the 4 to 20 milliamp output is working and capable of going the whole range. But a type of error that wouldn't be found by that would be corrupted memory for the microprocessor. So let's say there's external memory storage, and corrupted memory is definitely a failure mode of memory allocation, and many times it's only checked or compared, or the diagnostic might only be run on power up of the device. So many of the proof tests will, for a smart transmitter, will be, put it through the startup routine or cycle the power, because there's a lot of background diagnostics that run all the time, but there are some diagnostics that only run on startup. So that would be an example of certain failures that only happen if you cycle power. But the safety manual will tell you that. Should tell you, often it'll give you a type 1 and a type 2 test. Whether or not you would get 90% without cycling the power and running all diagnostics would be a function of the specific transmitter design. What regime should you have in place to test and check the integrity of the automatic diagnostics? That's a good question. Now, by requirement, 61508 says that your diagnostic can be no more than 1 SIL level below the safety functions of testing. So if you're having a SIL 2 safety function, you have to run that in a SIL 1 environment or higher. So you couldn't use an automatic test by a basic process control system to check a SIL 2 function. So most times the diagnostics are going to be in a safety approved environment. If you are implementing them in a non-safety approved environment, you would have to come up with a test scheme. So that would, conceptually, you could put SIL 1 or diagnostics for a SIL 1 safety function in a non-SIL rated device, and in that case you would probably try to treat it as a low, you'd have to have a test plan to validate those tests. I've not really seen it, I guess I've not really seen it done. I've seen the question come up on some SIL 2 SIFs, but at that point, you need better diagnostics to meet the PFD average, and you can't go to a non-certified box anyway, so they've got to be in the certified box. So most time it's addressed because they're implemented in a 61508 certified box, and otherwise you'd probably have to come up with something similar to a quality check or management for a SIL 1 type function. And you can imagine that puts a fair amount of overhead into your non-safety related equipment, which is another reason people shy away from that, because they're incurring a bit of overhead. How do you determine the proof test coverage during the SIL verification stage? It's going to take a combination of, tools like Excellentia have a proof test calculator in them that can take some of the generic data or some device-specific data, and it'll do that calculation. We are developing more, as the engineering evolves, more defined proof tests, and so some of that will have to be added in the future. Safety manuals and FMEDA reports should give you proof tests, recommended proof tests, and proof test coverage, so you can take that information and calculate it, and then you just have to calculate it out. But you want to be obviously everybody wants to be realistic, but it is a place that you don't want to put 0 in because you'll never achieve anything, and you don't want to put 100% in because that's not realistic. So it does take some time and effort. If we have a SIF with a demand rate of once per year and we set the proof test at every 2 years, it becomes a high demand SIF? Yes, it does. Absolutely. And now that's one of the, people want to push out their proof testing to 3 years and 5 years and only do them on turnarounds. And that's fine, but if you've got a demand rate of 5 years or something and you're pushing your proof test out to 3 years, you can no longer ensure that you're going to conduct multiple proof tests in between demands. So taking credit that you're going to find those dangerous failures is no longer valid. So that is an important consideration. What are examples of diagnostics for an on-off ball valve? Limit switches, yes, exactly. So you could have a limit switch or a rotary feedback position, or on a linear valve, a LVDT or limit switches, where you say, you give a command to maybe de-energize the output for 50 milliseconds, and you expect that that valve is going to move 5% within 50 milliseconds or 100 milliseconds or whatever you determine when you set it up. And so you say, I'm going to de-energize it. I should see that switch change state within this time period, and then you pass it. So that would be an example that I tripped the valve, it began to move within my specified time, and you reapply the power. So obviously that's all going to be automated, but then you'll get a pass-fail on the test. There are other things too, such as certain things like on turbines, they can do automated bottle checking if they've got redundant paths for the gas or the steam. There's a lot of different things, or batch applications where you can do some automatic startup and shutdown sequences that can give you quite a bit of information about the state of your valves. Would such one cell level below regimes apply to proof test regimes as well as automatic diagnostics? No. With a proof test, you're counting on the operator or the technician being involved, confirming the test ran correctly. So you could have the basic process control system cycle through certain things and generate an output, and then the operator could be validating or verifying that yes, that happened by looking at other sensor readings, by inspecting the valve. So with the proof test, you don't have that requirement. It's only the automatic diagnostic. And the reason you don't is because you have a person involved in the function, and they're kind of validating everything happened as it should. All righty, well, those were great questions. See if anybody's got any more, but appreciate everybody's questions. I think the input from the group really adds a lot to the overall presentation. Okay, well, we'll be posting a recording of this that can be downloaded and viewed. So if you got any questions, you can email me or email Exida, and we thank you for your time today. Take care.